Hi everyone, my name is Sandeep and today I'll be talking about our paper, Robust Streaming Against Low Memory Adversaries. This is joint work with Krzysztof and Omri. Let me start with the standard model in robust streaming. We have a stream of m updates where every update changes one of n coordinates by plus or minus 1. At every time step I, the streaming algorithm has to output an estimate y sub I, which is required to be a 1 plus epsilon approximation of some function f of the underlying frequency vector so far. So the underlying frequency vector just records how many times each coordinate has occurred in the stream so far. So the main example in this talk will be the f2 estimation problem, which is just the sum over all the n coordinates of the number of times they have occurred squared. An adaptive adversary can design every update, which may possibly depend on all previous updates, as well as all previous answers of the streaming algorithm so far. Now one of the main open problems in this field is the robust space complexity of FP estimation with insertions and deletions, also called the turnstile model, as a function of the stream length m. So consider the p equals 2 case. For oblivious adversaries, we have streaming algorithms that require space log m. On the other hand, in the robust case, a long line of work has culminated in in adversarial robust streaming algorithms with space complexity roughly m to the 0.4 for the p equals 2 case. This represents an exponential gap between the oblivious case and the robust case. Now our take on why this happens is perhaps because there is a power imbalance between the streaming algorithm, which we typically think of having low space, versus the adaptive adversary, which can just memorize the entire interaction history so far and can thus use space that's proportional to the length of the stream. So we asked, can we design efficient robust streaming algorithms for, say, the turnstile F2 problem when we restrict the adversary to be roughly as powerful or perhaps even slightly weaker than the streaming algorithm itself? So to be more precise, can we design robust streaming algorithms for, say, the turnstile F2 estimation problem against adaptive adversaries that only have b bits of memory, and we require our robust algorithm to have space complexity that's polylogarithmic in m and n, thus matching the oblivious case, and polynomial in b? So this question remains open, unfortunately, but we propose some of the first steps towards resolving this question and propose some interesting models as well. We remarked that other beyond worst case streaming models have been studied, for example, robust streaming with advice or with bounded interaction, but perhaps they don't fully capture the adversary being adaptive to all previous time steps, which our model will. Okay, so now let me describe our model. So on the right hand side, we have the streaming algorithm. It takes in an update, right, the next update, and it has to output these estimates. Now, the estimate of the streaming algorithm is written in something called the estimate memory of the adversary. Essentially, it's infinite tape memory, and this just allows the adversary to fully read the previous estimate that the algorithm has given. The adversary also has access to unlimited fresh randomness at every time step that it can read. The adversary also has access to unlimited working memory that it can read or write to. Okay, so essentially the adversary can compute any function that it wants to output the next update to the streaming algorithm. The caveat is that after every step, right, after every update, we wipe the working memory clean, okay, and we redraw the fresh randomness. Now, the only way the adversary can save information across different rounds is through its persistent memory, which we limit to be finite. Okay, so the persistent memory, the adversary can both read and write to the persistent memory, and this is the memory again that is carried across different rounds. Now, if the persistent memory was also unlimited, then this would reduce to the standard adversarial setting, But if we, when we limit the persistent memory, we call that a low memory adversary. And this is the main model of our paper. Of course, if the adversary has no persistent memory, then we call it a memoryless adversary. Or if the adversary has access to no randomness, then we call it a deterministic adversary. So our first result is a robust streaming, our robust streaming algorithms for low memory adversaries. So consider any function f of the underlying frequency vector that outputs answers between 0 and 0 and alpha. Then we give a deterministic robust streaming algorithm against deterministic memoryless adversaries with space complexity log alpha times log mn times 1 over epsilon. Or if the adversary is allowed to have b bits of persistent memory, but still is deterministic, then we give a robust streaming algorithm with the overhead of 2 to the b. The proof is very short. Essentially what the algorithm does is every time it outputs an answer, it routes it to the closest power of 1 plus epsilon in this range 0 to alpha. And there are only roughly log alpha over epsilon different powers. So what that means is the adversary will be a function of only log alpha over epsilon times 2 to the b inputs, where the 2 to the b factor comes from the fact that the persistent memory can live in 2 to the b different states. So essentially the adversary can only give log of alpha times 2 to the b different inputs to the streaming algorithm, and the streaming algorithm can thus memorize, these coordinates exactly. So essentially what's happening is that the streaming algorithm can force the adversary to give a very sparse stream. So, that's nice, but maybe perhaps not so interesting. So what happens for randomized memoryless adversaries? It turns out a much more interesting behavior happens. So that our next result is we show that randomized memoryless adversaries can fool the black box use of many existing techniques, but perhaps not all, in the existing robust streaming literature, okay? So the theorem is as follows. There exists a randomized memoryless adversary for the F2 estimation problem, such that any correct streaming algorithm, even those that are allowed to use unlimited space, such that for any correct streaming algorithm, the adversary can generate a stream that has high density, meaning the number of non-zero coordinates will be at least a small polynomial m, as well as high flip number, meaning the true underlying F2 value will fluctuate a lot. Okay, and this is interesting because a lot of black box frameworks have polynomial. A lot of black box frameworks in the robust streaming literature have polynomial dependency in the flip number or in the density of the stream. And our results shows that if we use these frameworks in a black box way, we're not going to get a good space complexity. We're going to get a polynomial in M space complexity. We note that getting one of these two requirements turns out to be not so hard, either getting stream with high density or high flip number. But the interesting thing is that we can get both with a randomized adversary that has no persistent memory, okay? So the strategy is as follows. What the adversary can do is essentially only look at the most recent answer that the streaming algorithm gives, right? Because it has no persistent memory. Now, if the answer is small, smaller than some threshold t, the adversary will insert a random element between 2 and n, okay? And this essentially, the intuition is, this allows the stream to have high density. If the answer is between t and 1 plus epsilon times c, the adversary will always insert the element 1. If the answer is too large, right, larger than some, t times 1 plus epsilon to the fourth, let's say, the adversary will always delete element 1, and in between, the adversary will do a random action. So the precise, thresholds that we have defined is not so important, but the main idea is that is as follows. The stream ends up having high density because when the estimate the algorithm gives is small, we insert a random element. So we end up inserting many different unique coordinates in the stream. Whereas if the algorithm output ends up being too large, we end up decreasing the f2 value by decreasing the coordinate 1. And in between, we do a random action, right? We have some sort of a random walk. And because random walks fluctuate, right, they go up and down, it turns out this also means that the flip number will change a lot. Okay. Sorry, the flip number will be high because the underlying f2 answer will change a lot. So now that we know that randomized adversaries are interesting, we give an algorithm that can handle them. Okay, so our main theorem is as follows. Given any order invariant oblivious streaming algorithm A that uses space A, we give a randomized robust algorithm for b-bit low memory adversaries using space that has an overhead of 2 to the b times log alpha over epsilon times log m factor. Okay, so you may wonder what is an order invariant streaming algorithm. Essentially, it's a streaming algorithm that doesn't depend on the order of the streaming elements. It only depends on the state of the true underlying frequency vector. So for instance, linear sketching is an order invariant streaming algorithm. These notions have been studied in the past. For example, a path-independent automaton of L and W. Okay, so our main idea to prove this theorem is to reduce to the case of what we call a stream merging adversary, and then use something called a computational path framework, which is an existing technique in the robust streaming literature to handle stream merging adversaries. We briefly note that our main result has other downstream applications. For instance, F2 estimation, robust F2 estimation against b-bit randomized adversaries. So now let's prove our main theorem, or give a high-level proof. So let me define a tau stream merging adversary. Essentially what this adversary is it generates tau oblivious stream before the interaction with the streaming algorithm starts. Sorry. And then at every time step, the adversary can be fully adaptive. It's not constrained, except that the update that it picks has to come from one of the tau oblivious streams that it generated. Okay, so for instance, in time step I, right, let's say the adversary picks stream 2. It has generated 4 streams in advance. It has to pick the next update in stream 2, but it can make this choice however it wants. And the main idea is that, well, if the streaming algorithm is order invariant, then it turns out that the only thing that matters is how many times the adversary has picked from stream 1 or how many times it has picked from stream 2 and so on. And it turns out, a simple combinatorial argument shows that there's only m to the tau different different states that the order invariant streaming algorithm can be in. So we can just union bound over all these, m to the tau different underlying frequency vector that the streaming algorithm sees. So that means we can amplify the error probability, of an existing streaming algorithm that's order invariant from delta to, let's say, delta over m to the tau, and pay an extra, polylog factor times tau overhead in the space complexity. And now the next step is to say, oh, well, it turns out that lower memory adversaries, meaning adversaries that have b bits of persistent memory, actually end up being stream merging adversaries as well. Except we have to figure out what is the right value of tau here. Well, now let's dive a little bit deeper, right? How does our adaptive adversary generate a stream input? Well, it sees the estimate y, and it looks at it's also a function of the current state of the persistent memory. So based on the current state of the persistent memory and the current estimate that it sees, it generates from some fixed distribution, right? That depends on the generate from some fixed distribution. So what we can do is we can do a thought experiment. Let's say, let's just of all the distributions that the adversary can possibly generate from throughout the throughout its interaction with the streaming algorithm, let's just generate all these samples in advance, and then the streaming algorithm while it's interacting, while, the adversary, while it's interacting with the streaming algorithm, it's not going to generate on the fly. It's just going to look up the next sample from the right distribution. So all we have to figure out is how many different distributions can there be throughout the adversary's interaction with the streaming algorithm. It turns out the combination is the same as before. It's 2 to the b, which is number of different states of the persistent memory, times log alpha over epsilon, which is the number of different estimates that the adversary will see, assuming the streaming algorithm will round its output again. So that means we can roughly set tau to be 2 to the b times log alpha over epsilon, and we can use the previous theorem that we have about tau merging adversaries. So one interesting remark is that our adversary cannot actually maintain the exact time, because it takes log m space to maintain the exact time, and 2 to the log m would be poly m. But of course it can maintain an approximate time using Morris counters. So an interesting open question is, what if we allow the adversary also access to the current time, or the current round, the index of the current round that the adversary is in. We also know that there's an interesting work on a problem called missing item. There are many interesting works on this problem called missing item finding. It turns out our results don't apply here, because missing item finding turns out to not be an approximation problem, right? The answer is not a number between 0 and integer between 0 and alpha. It's about outputting a set, or it's about outputting a set. So the output is essentially exponentially sized. So our results don't apply here. So now let me conclude with some nice open problems. So then perhaps the main open problem is, can we reduce the 2 to the b dependency to poly b dependency? And this, if we manage to do that, this may allow us to make some progress on the original robust streaming setting as well. And the current reduction that we have to stream merging the adversary may be very lossy. So that's a potential, improving that reduction is a potential line of attack. And another interesting open question is, what can be done for problems with an exponential range, right? Where this log alpha factor would actually be quite large. For example, outputting the set of heavy hitters. There are even more open questions, right? For instance, we showed a randomized memoryless adversary that can create both the high flip number and high density for the F2 problem. Can we do the same for the F0 problem? We think the answer is no, but a proof would be nice. Another question is, can a recent work by Woodruff and Zoe, which introduced a new technique for robust streaming, can they handle our low memory adversaries for, let's say, the F2 problem? That's also an interesting open problem. And lastly, right, can we improve our polylog dependencies, or can we improve our results for other specific choices of the underlying function f? Thank you so much. And if you have any questions or comments, please don't hesitate to contact us. Thank you so much. Bye.